Okay, thanks for taking the time to join this call. Uh, I've missed, I don't know what was discussed a bit like at the beginning, but so maybe what I can present. So I'm a research engineer with IC3 for the past 6 years. IC3 means Initiative for Cryptocurrencies and Contracts. It's a consortium of universities, headquartered at Cornell Tech, New York. Uh, okay, so. And for the past 4 years, we've been working a lot with Intel SGX mainly. But this is in the context of blockchain protocols. So a lot of people here are familiar with that. So Secret Network, Oasis Network, Fala Network, and there's so various protocols that make use of trusted hardware to provide some kind of security guarantees, right? So, and the main idea is, right, you can send your computations to a node and in this network, and the node will guarantee you that it's going to execute the computation as you expect, and including processing confidential data. So, and in the context of working with this uh, IntelliJ especially, um, it became clear to me quite quickly that there's an issue with the root of trust, right? So depending on what your trust assumptions are, you have this situation that you have to be extremely careful that you don't want the node operator to attack their own hardware to gain some benefit on the system you're working that they're participating in it. So to give maybe the easiest example for this is like multiple years ago, I think around 2016, people thought, I think it was a project by Intel and IBM called POET, Proof of Elapsed Time, and they thought they would replace proof of work by using a T. And the idea is that rather than try to brute force the hash, they would just like wait an arbitrary amount of time, and that arbitrary amount of time was uh, enclave, right? Like a software program that was run in the secure enclave. So the trust assumption here was that, yeah, the miner here would be able to provide you a proof via attestation that it ran the code that you expect. That means that it did wait an arbitrary amount of time and it was lucky enough to win this little lottery, and then therefore it could get the block reward. But they realized very quickly the problem with that is that people now were incentivized to break into their own hardware. And so this was put aside as and was seen as something that could not be used because therefore there were limits to T's in the cryptocurrency sort of application context because the amount of money that was available if you attack the system was too high. So consider that for a moment, right? So we have this problem that unlike with mathematics, like zero knowledge proofs, MPC and FHE and so on, where we have some security guarantees that you would have to break the mathematics to break the system. Here we have this more like sort of like blurry or somewhat uncertain situation where it's not clear, right? Depending what kind of equipment you have access to, depending your expertise, you may be, and if you have physical access to the device, right, you may be able to break it. And so Intel SGX and some of the other systems, the way they are designed, they don't assume like these sophisticated attackers, first of all. They assume like someone who has like limited expertise and limited equipment. So basically a bit like a hobbyist. Like some of us are the same with our phones, unless you're an expert and have the laboratory, you're not going to be able to hack into your phone at the hardware level. So this creates this big problem because, like, again, the money aspect here of blockchain ecosystems is such that the incentives may be really sufficient for people to really try to attack these chips. So that's the angle I've approached the T's, and this led now to if I fast forward, to now, uh, there's actually 20 plus years of research that is not leveraged right now with the current T's that we're, we're kind of stuck with. By the way, right? Yeah. So, okay. So if people have any question, you can stop me, right? Because I don't have like a sort of like, I could present some slides that are from this summer, but some people have already seen that in this talk. So, and it's not going to be, uh, maybe that useful. So we're in this situation right now in the blockchain ecosystem that we don't have anything better than SGX and TDX and AMD. And we're kind of like people do like very smart work to work around these limitations. However, it is it makes sense to ask the questions, can we do better, right? And this is where it gets a bit complicated because we have now to really dive deep into how hardware is manufactured, how hardware is designed, and looked at what are the solutions that are better that we could use. But they are uh, multiple solutions that would be better. And again, okay, so we have this problem too that hardware cycles to manufacture hardware is much longer than software. So a lot of people, and I think that's what has happened in the past few years, people are reluctant to go in that direction because you won't get any return or benefit within, you know, a couple of years. Yeah. So I don't know if that's clear as a sort of like setup, right? But to reiterate, right? So we have this problem that, right, trusted hardware depends on this root of trust. The root of trust right now with Intel SGX, TDX, and so on is such that it cannot be it's not protected, it's not secure against physical attackers. So the best solution to that for now is that people either their protocol is there's not much money involved or not the incentives to break the hardware is not there, which creates a very difficult situation because we don't even have an economic model for that, so that we can have like some kind of mechanism design or game theory to really design systems properly. The other option is that people rely on cloud infrastructure, and then you expect the cloud provider to protect the hardware against physical attacks. So that's the situation we're at. Now, if we look at again, I mean, there's a Torben who's in this call right now, who's with Sylvain and Simple Crypto. So there are like groups already that are working on open source hardware, on hardware that is secure against physical attacks. So I think the idea here is that the Web3 community, the blockchain communities need to, there needs to be some kind of synergy that is stronger with the hardware research world and industry so that we can work together to develop chips that are more adapted to what we really need in terms of security guarantees. I would like maybe it would be more useful if people can ask questions here, so it's more interactive. Unless I just pull up some slides or some document, because I prefer like that. It's really, yeah. Does it make sense?
It makes Julio, please.
Yeah. Maybe just one prompt for you, Sylvain, is what are QTs?
Well, in the process of looking at this, I just like, okay, because we're the problem here, there's multiple angles to that, like, but one angle is like in theory or in right, because we're in this blockchain context, right? So on one hand, you have all this mathematics that provides us really super high security guarantees as to whether a protocol is going to be secure or not. And then we are using these T's in conjunction or as an alternative to some of, or people combine, okay, with the mathematics-based cryptography. And with T's, it's a bit more difficult to know whether it can be really secure or not. And the idea of QTs was that to ask the question, okay, can we have a model so that we know what are the physical limitations of T's in terms of whether they can be attacked or not? And as far as I understand right now, it's like truly secure T's that are secure against physical attacks, like if you apply this some kind of same mental rigor that we applied to cryptography, it's just not possible. You cannot have a proof, okay, unless you go to quantum device. So the Q and T was a bit to point that we maybe at some point we'll have to use quantum devices for having the same sort of like high security that we want to have. But there's a bit in between that. Before that, what you can do, you can leverage, if I'm talking about now the core problem, right, that you don't, okay, because I want to be careful because the way when we approach this, it can look very like far-fetched, okay, but it's not so far-fetched. But if you approach it like, because if we try to explain this in simple ways, but again, right, you have a physical device, and the problem is that there's a hardware key that is embedded in that hardware device, and you want that hardware device to be in the hand of someone you don't trust, and not be able to extract that private key. So this creates this really difficult situation that, like, how do you do that? That means, because if you're able to write the key, why couldn't you read it? All right. So we need somehow to be able to have a key embedded in a physical device, in a hardware device, that needs to be generated such that no one knows what this key is. And once the key is in the device, no one is capable to extract it, no matter how much money they have and how much expertise they have and how much physical equipment they have, and no matter how sophisticated they are. So again, right, I think in theory you have to go to quantum physics for that. But if in practice, like, we have this thing called physical unclonable functions, which is like, at least in practice, is the best thing that we have and can provide us like extremely high security guarantees that the device will be secure against such attacks.